It should be recording now. Does anybody see that indicator?
Yes, sir. I see it.
Awesome. Thank you very much. Okay, so like I say, as I said, starting next week, we're going to be meeting face to face. Again, I want to remind you, Mondays and Wednesdays will be lectures. The location will be NSCW 1244. And that's NSCW downstairs, right out of the parking lot. You walk into 1244. It's like the third or fourth classroom on the right, downstairs. Tuesdays and Thursdays, again, all we do those days is lecture. Tuesdays and Thursdays, we meet in NSCE, the science building that's adjacent, 1118. Okay, and that'll be for lab. Just want to let you know. So that's starting next week. We're going to be on that regimen. Okay. All right. So today my intention is to cover chapter 1. We're not even doing physics really yet. Physics really starts on chapter 2. Chapter 1 in most books is usually, there's not much to say. I mean, usually it's covering units and that's about it. It's more of kind of a pass through, overview chapter. Not so in this book. Putnam and Johnson, yes, you will have, basic concepts like units, but we're also going to cover very important mathematics in that is necessary for this class, and that is vectors. And when we cover two-dimensional vectors, we'll have to remind ourselves of trigonometry. So tonight's lecture is really more of a math class than anything else. All right, so we haven't really gotten into physics yet. We have to really develop what we need in order to be able to do physics. So as a starter, so again, chapter 1, units and vectors. I'm going to, as I always say, oftentimes in my when I do these online lectures, I talk about a real estate problem, and that I always have a space issue. So I'm going to try to have as little on my whiteboard as I possibly can because I'm always fighting for space. So talking about units, regarding units, you have to have a system that is generally recognized across the world. So basically a system of units is one that or in which measurements are reported. Or I should say it's one that is agreed upon across the world, and it is used to report measurements. So I shouldn't have to tell somebody in France, for instance, what a kilogram is. They should know what a kilogram is. Right. And so, yeah, I'm starting off basic in this class. But again, I say system of units is one that is agreed upon across the world and is used to report measurements. Any kind of measurements that you make, there is some sort of a unit that is reported. Now, our typical system of units throughout the world is called Le Système International. All right. It's French. We oftentimes say SI. I'll write it down in a second here. So this is a unit that everybody in the world uses except the United States. And so we oftentimes refer to it as a metric system. Sorry, I got issues here. All right, hang on. Okay, so the system of units used throughout the world is officially it's Le Système International. Oftentimes we refer to that, I think that's no either. Refer to that as SI. So the French people, French language and Spanish language, they put the adjectives after the noun. English, we put the adjectives before the noun. So we say Le Système International, and basically it's International System of Units. All right. So we refer to it as SI. We also refer to this as the metric system. All right. So Le Système International, that's actually a Y there. I have a little light spot there. Anyway, that is what we use throughout the world. I've kind of read it again so that that light spot's not in the way. Sorry. All right. So again, Le Système International. Or SI. And so all units really break down in a very fundamental way. So the SI units, they all break down. So all SI units, or all units, I should say, break down in terms of length, mass, and time. Okay, length, mass, and time. All right, and so it's very important, and that may not as we get further on and in more advanced studies, and that's going to happen very quickly. We kind of forget about that, but if you look at sort of length unit in SI is the meter. The meter is very precisely measured. It's based upon the speed of light, and the speed of light is exact. So the meter, regarding the the officials at NIST, National Institute of Science and Standards and Technology, they're the keepers of the units, and they have defined the meter exactly in accordance with the passage of the speed of light. Think from a laser. You have mass. That's in terms of kilograms. So, and we oftentimes abbreviate that as kg. Meter is abbreviated as M. Then you have time. And that is seconds. And time is measured also, actually time is measured according to the vibrations of a cesium atom, according to NIST. So again, but it's very, very precisely measured. All right. And so, so if you look at, say, if we kind of go a little bit further, a little bit ahead, like say chapter 4 for a moment, we'll talk about force. Now, force, we have special unit. Let's see if I can try to avoid that light spot there. Sorry. Try to control the lighting in the room here. So we have force. And the units on force, we oftentimes say F. Well, units on force, we have a law called Newton's second law. And I'm going to write it in a kind of a real, kind of a basic way. There's going to be a more official way of writing it when we actually get to chapter 4. F equals ma. Force is mass times acceleration. If you look at that, the mass is a kilogram. The acceleration is a meter per second squared. So it's a mass per length per time squared. We have units like that. We refer to that as a Newton. So the SI unit of force is the Newton. If you think about so many newtons, while Newton is nothing more, if you break it down, it's a mass times the length divided by a time squared. All right. So for instance, we have force. Another concept we're going to study is energy. So we're going to study something called work, particular form of energy, for instance. Now, work, again, I'm going to be very basic here. Sorry, I got this light spot here. I try to avoid it somehow. Afraid if I do, let me see if I can adjust this this a little bit here without completely destroying everything. Sorry. I got this light spot that's driving me crazy. All right, let me adjust things a little bit. There we go. All right. Should be able to avoid it a little bit better now. All right, so you have, for instance, work is a form of energy. And so, in a very simple sense, once we understand force, work, W, we can say is the force times the displacement. All right, and so force times displacement. Now, again, there's a more advanced mathematical concept. I'm just giving you it very sloppily right now for chapter 1. Well, look at force. Well, work is an energy. So work is an energy. And we're looking at a Newton times a meter. What's a Newton? I know what a Newton is. That's kilograms meters per second squared. So that's a kilograms meter per second squared times a meter, or a kilogram meter squared per second squared. And again, as you can see, the unit of energy is generally in terms of length, mass, and time. Here I have a length times a mass times a length squared divided by a time squared. So altogether, in the most basic sense, all the units you can think of in physics are generally described in terms of length, mass, and time. Right? And so now I've been talking about these SI units. We in the United States use a little bit different unit system. I mean, now generally, if you are a professional scientist, you're going to use the SI system. In the United States, we oftentimes use the imperial system, as it's usually referred to. And so length might be feet, mass might be pounds mass, time is the second still. Your force would be your pounds. Now, sometimes it's pounds mass, sometimes the unit of mass in the SI system is actually called the slug. Now, again, we generally don't use English system. Very seldom will we use, I say the English system, I'm sorry, that's oftentimes how I referred to it until I had a couple English students in my class who told me that they did not use that system in England. They actually refer to it as imperial. So the official word of saying it is actually the imperial system. But we will not use the imperial system very often at all. I mean, very, very seldom will we use it. I mean, you should, given that you live in the United States, you should be familiar with it. Now, you may be familiar with it because that's part of your culture. Our culture is based on, lengths are in, are in feet or miles or yards. Our pound, our forces are in pounds. I mean, that's really ingrained in our culture. And it's hard to break. Back in the 1970s, back when I was a kid, there was actually an effort put forward to try to make the United States metric, and it didn't go well. And so, even though there was an attempt, the United States is probably just going to remain in the imperial system, even though you as a practicing scientist will actually use the metric system. And oftentimes what happens at the very end, you'll convert from an imperial system, I'm sorry, metric system unit to an imperial unit so that you can talk to your customers. All right. So again, these are, I don't have to, these are units that are understood by everybody in the world. Again, this is an agreed upon set of units, particularly the metric system. I don't have to explain to somebody in France or Germany or China or something, what is a kilogram or what is a second or what is a Newton. I don't have to explain that. It should be understood that when I tell somebody that something is 3 newtons of force, everybody in the world should know what that means. I should not have to explain that further. So that's where we all are speaking the same language. Okay. That takes me to conversions. Now I gave you, there's a document that one of the many documents under files is one that does deal with conversions. Very useful. The metric system is nice. So the metric system is a base 10 system. So the most basic thing we have a base 10 digits. We have 0 through 9. You make any kind of number that you like, a real number based upon 0 to 9. You have 10 fingers. Essentially your digits, the digits on your that you use are a base 10 system. It's a natural system for us. Well, metric systems are also a power of 10 system. All right, and so you take something, you can just you can literally put a prefix on it and convert. So for instance, we have all these various prefixes. So you can say, I have 10 to the negative 9. We call that nano. Actually, let me go even further than that. 10 to the negative 15. That's 0.0 with 14 zeros and a 1. 10 to the negative 15. Very, very, very small number. In fact, that's a number that is typically the order of the size across the nucleus of an atom. This is referred to as femto. So you might have, say, a femtometer. That's 10 to the negative 15 meters. You go 10 to the negative 12. That's called pico. You might have, let's say, a picometer, a billionth of a meter. Actually, I apologize, a trillionth of a meter. 10 to the negative 12 meters, a trillionth. You can have 10 to the negative 9. That's nano. So like a nanometer. That's like the bacteria, for instance, and viruses are measured in terms of nanometers, particularly viruses. 10 to the negative 6, that's micro. We use a Greek letter for that usually. We have little mu. The Greek, this is called the Greek letter mu. Spelled M-U. It's pronounced like a kitten says mew. All right. So again, this is a small Greek M. So this is used not only every letter of the alphabet to describe variables, we have to actually borrow other people's alphabets, particularly the Greeks. And so there are many uses of the letters of the Greek alphabet. Okay, that's micro. You go to the 10 to the negative 3, milli. Like a millimeter, little m. 10 to the negative 2, centi. Like a centimeter. 10 to the negative 1, decimeter, for instance. 10 to the 0, which is 1, that's the meter itself. Or that's just 1. If I go 10 to the 3rd, kilo, like kilometer. 10 to the 6th mega. We usually use capital M for that. Now, I don't really see mega meters used very often. Oftentimes I'll see stuff like frequencies, like megahertz. So mega means million. You know, I hear, oftentimes people talk about megabucks, $1 million, and usually capital M for mega. 10 to the 9th. 10 to the 9th is, let's see, that would be mega, that would be giga. And actually, I probably should capitalize this. And again, that kind of, I oftentimes see that for frequencies like gigahertz. All right. 10 to the 12th, we started getting big, like, and I never thought when I was a kid or when I was in my 20s, I never thought that I would ever see this applied to computers, but it is true. I'll see stuff like, and sometimes I'll even see gigabytes, if you will. Here, this is called tera. And we actually can have, let's say, terabytes. I never thought I would ever see that. And so, things have gotten crazy. So I think 10 to the 15th was like atto or something. But again, these are all distinguished, levels, orders of magnitude that literally can be converted to very, very easily through powers of 10. Very easy math. So for instance, if I say I have so many kilometers and I want to understand how many meters that is, as an example, the conversion is quite simple. Again, this hopefully is a review to a lot of you guys because we're just getting started. But let's just say, for instance, I want to understand I have 3,500 meters. That's my length. And I want to understand how big that is in kilometers. I say, okay, well, I'm going to multiply this by 1. I'll multiply it by 1 in a very special, suggestive way. And that is that I know that a length of a kilometer is the same as 1,000 meters. Right? That's basically 1. Whatever I call the length of a kilometer, and I say the length of 1,000 meters, that's the same thing. I'm dividing by a certain length over a certain length, the same length over the same length, that's 1. And so this is called the factor ratio method. You probably learned that in your high school chemistry class or maybe your college chemistry class. But this is a way of converting. And then I do this quickly, 3,500. This gives me about 3.50 kilometers. So if I have 3,500 kilometers, if I have 3,500 meters, that's the same as 3.50 kilometers by doing what? By essentially multiplying by the conversion factor. And how do I know the conversion factor? Because I know these powers of 10. I know these powers of 10 equivalencies from the metric system. So it's very easy to go from one conversion factor to one unit to another. Where it gets a little bit more complicated is when I have to go and convert from, let's say, the imperial system to the SI and vice versa. This is all within SI. And again, for 99% of this class, we're going to be working in SI. But again, you do live in the United States. You will, most of you, if not all of you, will have a job in the United States. And you'll have to eventually, at some point, the very, very end, when you go serve a customer, you're going to have to speak to that customer, communicate with that customer in the imperial system. And so there's going to be a little bit. I had a question here. Did anyone catch what was written for 10 sub 0? Can you ask that question? I'm sorry. I saw something in chat. Whoever. Oh, just meter. That's 10 to the 0. Okay. Did you hear what I said though? The person initials KK. Is that understood? Okay, thank you. I have my chat open as well to make sure I catch any chat questions. And feel free, anybody, people whose microphone is working, if you do have a question, please, feel free to interrupt me. So, okay, so again, we're just kind of doing some basic just housekeeping right now to get ourselves started this week. So now again, going back to the imperial system, it's a little bit, and these are things that you'll notice that as I mentioned, we're working within the SI system. All I have to do is multiply or divide by powers of 10, which I don't even need my calculator for that. That's just moving decimal places. But you have the imperial system. And unfortunately, there you have to kind of remember things. And so, for instance, in the imperial system, you know that 1 meter equals 3.281 feet. And there's no ifs, ands, or buts about that. I mean, that is what it is. 3.281 feet in a meter. So, for instance, if I were to say I want to figure out, I'm 6'1". So if I want to figure out what my height is in meters, if I was telling a European how tall I was, 6'1". Let me just kind of do the calculation real quick. 1/12 is about 0.083. So I am 6.083 feet tall. And I want to figure out how big that is in meters. I would say, well, let me see here. 1 meter is 3.281 feet. And notice, oh, well, feet cancel. Again, I have this unit conversion. How do I know what goes in the numerator? What goes in the numerator is what I'm trying to convert to. And the denominator is what I'm converting from. And you notice that mathematically, algebraically, the feet cancel. So if I work that out, 6.083 divided by 3.281 gives me 185 or 1.85 meters, 185 centimeters. So I would tell a person, say in Europe or some other place other than the United States, that I am 1.85 meters tall. As opposed to 6'1", right? But again, all I have to remember, this number is not natural. This is not a power of 10. This is just, the way it is. We have this system of units that we have for whatever reason, this imperial system. There's other things that we have to kind of remember in the system. So for instance, we must know that a foot has 12 inches. And there's no rhyme or reason as to why that is true. But we also talk about length units, say, of inches. We know that a mile is 5,280 feet. So you might have to convert, let's say, from you might have to convert, let's say, from miles to feet, for instance. Let's just say I want to know I have 2 miles. And I'd like to know, or say I'll make this a little less boring. I'll say 2.5 miles. I have 2.5 miles and I want to know how many feet that is. Well, let's see here. I have 2.5 miles and I say, well, I know that there are 5,280 feet in a mile. So if I want to do that, I would take 5,280 and multiply by 2.5. And I'd get 13,200 feet. So I have to convert within the imperial system, or I might have to convert between the imperial and SI. What's another unit that I might want to remember? Well, let's see, I'm not going to go too deep into this, but let's say when we talk about forces, we haven't talked about forces yet, but we will know that a pound is 4.4 448 newtons. That's another conversion. No rhyme or reason about it. Why is that so? Who knows? But it's just, that's just the way the imperial system developed. And then the SI system, we had to figure out how one converted to the other. All right. So again, you have to be able to do conversions. Now, we're not going to do a lot between the imperial system and the SI system, but we will actually convert a lot within the SI system. Any questions so far? I'm about to leave units. Go into vectors. All right, no questions. All right, so now let's go talk about vectors. All right, so in your life before going to physics, you've been content with just dealing with real numbers. All right, and so but I will claim to you that whether you realize it or not, when you're talking about a signed SIGN ED real number, you're actually talking about a vector. So there are two in physics, or I should say in college physics. I mean, in physics, we have other kinds of mathematical objects as well. But in this class, physical quantities come in two forms. And those forms are scalars and vector. All right. I'll start with a scalar. Scalar is a number or quantity that only has a magnitude. A vector is a quantity that has a magnitude and a direction. So there are two parts to a vector. A vector has basically, we refer to as a length, how big the vector is, what its magnitude is, its size, basically, and its direction. All right. And so whereas a scalar only has a magnitude. So let me talk about a vector. Let me start off with one dimension. Okay. So and remove ourselves into two dimensions in a moment. So in one dimension, we only had really, well, let me back up for a moment. In two dimensions or in n dimensions, but we'll say right now in two dimensions. I mean, this class, some problems will actually require three dimensions. Two dimensions, we express physics in terms of a Cartesian coordinate system. That's famous for saying you have an x-axis and a y-axis. Okay, we're used to that in algebra. In our algebra classes, we have an x-axis and a y-axis. Officially, that's called a Cartesian coordinate system, named after mathematician Rene Descartes. All right, so Descartes was a mathematician and a philosopher. The story goes he was lying on his bed looking up at the ceiling. And he was watching a fly walking around the ceiling. And he asked himself the question, how can I systematically locate this fly? And he came up with the system that you study in your algebra class. He says, well, if I were to define an x-axis and a y-axis, let's say my fly is located someplace in space, and I agree that this is what I call my origin, then I can go so many units in the x direction, and I can go so many units in the y direction, and I can locate this fly. Now, every single map you've ever used is a version of this kind of a Cartesian system. You know, you go to, let's say, Disneyland or something. You say, I'm going to find out where Tomorrowland is. Well, you might say something like this. Maybe down here, you might have A, B, C, D, E, or something like that. And up here, 1, 2, 3, 4. And it might say, oh, Tomorrowland is located at C3. Oh, okay. What does that mean? I go C along the x-axis and 3 along the y-axis. And that is where Tomorrowland is, or that is where I can find some Toy Story ride or something. I mean, essentially, I can locate this on a map, and any kind of map you have is going to be a form of Cartesian coordinate system. Now, unfortunately, with the way this textbook is, the way it's written, is I have to kind of put the cart before the horse. I actually have to talk about things before I really want to talk about them. When I go and talk about mathematical review, I oftentimes want to do it while I need it. So when I go and talk about two-dimensional vectors in this class, I don't need two-dimensional vectors until I get to chapter 3. What I'd like to actually do is talk about two-dimensional vectors when I get to chapter 3, not before I get there. So, and why I say that is because I have to introduce to you physical concepts before I really want to. I'm not going to go very far into this, but I'm going to talk about a couple of physical concepts first, and then we'll talk about them again when we get to chapters 2 and chapter 3. For right now, though, I want to talk about one dimension. I want to talk about a vector in one dimension. In one dimension, my Cartesian coordinate system looks like what I refer to as the real number line. So my Cartesian coordinate system is one-dimensional. And I can call it X if I like. And one of the things you have to do when you define a coordinate system is you have to define an orientation. And what I mean by that is you have to have an agreement that you specified, you state, where you state what is positive, what is negative, what is increasing, what is decreasing. So I'm going to refer to anything to the right in my definition of a coordinate system as positive, and anything to the left as negative. All right, so anything, let's say if I have motion, any motion going to the right, I'm going to call that positive motion, positive velocity, for instance. Anything heading to the left, negative motion, negative velocity, whatever you want to call it, negative force. Basically, anything to the right, positive, anything to the left, negative. I have to do that. I also have to define what I refer to as the origin. What am I calling 0? This is not. There you go. This is tilted. Sorry about the whiteboard here. Okay. That's supposed to be kind of in the center here. Okay, what am I calling 0? All right, and so let me make my coordinate system a little bit bigger. All right, call this positive, call this negative, and I'll call this X, whether I need to or not. And what I want to try to do here is I'm going to talk about very, very briefly, just one physical concept that I really don't want to talk about until chapter 2. And so this concept is, so first and foremost, I need to kind of go back even further. So in this class, if we want to position, put ourselves in terms of a chronology, we're pretty much at the year 1500 in this class. Okay, so in 1500, right around that time, there was no science. Okay, now you might say, well, that's interesting because people had some sort of technology. They had, there's weapons and things like that. But really, when I say this, there really wasn't any kind of a scientific way. Like, for instance, people can just mix things together and they form a new substance. They just remember what they did, and then they can do it again. You don't have to understand chemistry to make a batch of cookies. If somebody else made a batch of cookies, all you have to do is get their recipe. Whether you understand what is going on in the chemistry of baking those cookies, it doesn't matter. You follow the recipe, your friend, Mike goes off and makes a nice batch of cookies. Well, you could do that too, provided you have Mike's recipe. All right. And so again, it's things were discovered accidentally. It's an old kind of a funny little commercial I saw one time. It was two guys walking along, they're gonna run into each other in a corner. One guy had a jar of peanut butter, and the other guy had a chocolate bar. And they're gonna, they don't even know about each other, but they're gonna collide. And some of the guys' chocolate bar got into the other guy's jar of peanut butter, and then some of the peanut butter got into the guy's chocolate bar, and they accidentally discovered Reese's. They discovered, hey, this tastes good together, right? And this is kind of how things were for thousands of years before they had science. All right. So as I said, we're in the year 1500. Well, in the year 1450, maybe 1452, roughly around there, you had what was called the Gutenberg printing press. I would refer to this as probably the greatest invention in history. And why I say that is, before the Gutenberg printing press, there were no books. You imagine for a moment, you go to your house or whatever, you have books around you. There were no books prior to the Gutenberg printing press. The only book that really existed in any form was the Bible, and that was printed by hand scribed by monks in monasteries. There wasn't even widespread literacy. Now with the printing press, you could actually mass produce books. So initially, the Catholic Church was, a very dominant force back at this time, and they're like, great, we actually now have books, and we can mass produce Bibles, which is great, but the thing about it is, the Catholic Church, may have been very happy about the ability to put a Bible in everybody's home, but the thing about it is, yes, you may be able to mass produce books that you like, but there will also be books that are mass produced that you don't like, or maybe don't agree with. So at this point in time, you had, from nothing, all of a sudden now you have great, again, oftentimes things take about 50 years to finally, to finally see any kind of an effect, any kind of effect, from a cause in society. And in about 50 years, you have another, generation or two. You had challenges to science, politics, and religion. Part of it was, a lot of people said, is the Catholic Church, is it truly the is it truly the true religion, or or do we disagree with them? So yeah, the Protestant Reformation happened right around, I think it was 1501, pretty much on the dot. You know, you had Martin Luther posting his 101 Theses on the Bishop of Rome's door, saying, we challenge the concept of supreme authority of the Catholic Church, for instance. And then at the same time, you had people challenging politics. Is a monarchy, is that the right form? Well, there were publications made about democracy, and there's also publications made about form of government that I don't agree with. That's communism. But again, both of these were published. And now you have democratic, nations, and you have communist nations. As a result, you don't have a lot of democracies, and I'm sorry, you don't have a lot of monarchies anymore. Well, science, you also have a whole new approach, and we'll talk about Galileo starting next week, of people challenging, making challenges to science, asking questions. And so the Catholic Church dominated science, and so they had, the Greek philosopher Aristotle was to be taken as what he said was in fact. And Aristotle was taken, and basically people said you're not to question Aristotle's teachings. Aristotle's teachings are final. Oh, Galileo questioned them, and we came up with what's called the scientific method. And so in so doing, Galileo had to actually, and then following him is Isaac Newton, had to actually develop the language and the concepts necessary to even describe the mechanical system. Remember, mechanics is the theory that governs bodies or systems in motion, in all three modes of motion. And that's translation, rotation, and oscillation in all three major states of matter: solid, liquid, and gas. The first thing you have to do is state, in the most basic sense, the state where something is. So when I was teaching this class a few years ago, I've taught it many times, every year, usually 2 to 3, about twice a year, usually, for the last 8 years. But one particular year, as I was driving to class, I noticed, as I was looking across the street, there's a new development of an HOA being, it's going to be a multi-million-dollar homes. Some guy sold off his ranch, and essentially this was going to be made into many homes. It was a huge pasture, and it's going to be made into many homes, and very wealthy homes. And when I looked across, all I saw were bulldozers pushing around dirt. And I thought, isn't that interesting? There's the promise that there's going to be these beautiful, multi-million-dollar homes. But right now I look across the street and all I see is a bulldozer pushing around dirt. So in this class right now, that's where we are. We're going to have two beautiful theories, plus waves. We're going to have a theory of mechanics and theory of thermophysics by the end of this, and by July, by early August or end of July. But in the meantime, we have to ask the most basic questions of really pushing around dirt. So the number one thing we have to ask is, in a system that describes bodies in motion, I have to figure out a way of stating, where is the object? Again, I have to ask some very basic questions. And so what I need to do is, the first thing we need to do is to establish a coordinate system, right? So in a physical problem, we must first establish a coordinate system. We have to define everything. And that includes an orientation. All right, coordinate system, you need to tell me what's positive and what's negative. So every single measurement, every single physical phenomena that you can talk about is with respect to a coordinate system, pure and simple. That's the first thing you have to do. Now, what I have to do is I have to establish, where is the object? Again, asking the basic questions. Again, this class will get complicated or more, more complicated if some of you are, thinking that its concepts so far are, not too advanced, but they will be. Again, we have, every time you start a new theory, we start the theory of thermophysics, I'm gonna have to go back and again, scratch out dirt again, if you will. So we have to decide, we have to state where an object is. So we need a variable to describe the location of an object. So we call this the position. All right. The position is where the object is. Again, if I'm erasing too fast, please tell me. I'm just gonna, since I have a little real estate challenge here today, I'm gonna pretty much almost erase as soon as I write something down. So you will have this video available to you. So if you miss something, the video will be on YouTube tonight. So the position is a vector. Meaning that it has a magnitude and a direction. All right. So I have this coordinate system. Let's say X. I'm going to talk about position. So let's say that the unit is meters. Whatever I talk about is in meters. And I want to talk about an object that's going to be located, let's say 1, 2, 3. I'm going to be very methodical here or deliberate and call that positive 1, positive 2, positive 3. Let's say on the other side, I have -1, -2, -3, and I'm going to put this object. I don't know how it got to how it got to +3. We're going to say the object is located at +3. It's located somewhere in space. It's sitting here on a table or somewhere on the ground. And I'm saying, how do I locate that object? Just like Descartes asked, how do you locate the fly? Well, I draw in this case, my one-dimensional courses. I put a real number line, and I established to myself, for whatever reason, that this location, this spot right here is the origin. And I say, okay, I'm going to try to state a position. So I take an arrow and I draw an arrow from the origin to 3. And I can call that X1. I put a little hat on it. This little half hat is a vector sign. Okay, so this hat indicates that what I'm dealing with is a vector. That there is a magnitude and a direction. The magnitude is what? Well, the magnitude is the length of the arrow. It is as if I took a measuring tape and said, how long is this arrow? Oh, the arrow is size 3. The direction is to the right. And so what I can actually say is, in a sense, when you're talking about a signed number, you actually are talking about a vector. And so, again, it's not, when I get to 2 dimensions, it's going to be more complicated. But in this particular situation, when I talk about a vector x1, I literally will say it's +3. 3 is the magnitude. There's 2 parts of this number. 3 is the magnitude, and plus is the direction. Now, when you study algebra, you learn about absolute values. All right. And oftentimes I hear people, I even heard, my son was taking a math class, back when during the pandemic. And so I was stuck working from home. and he was in the next room over at the table working from home as well. And I'm overhearing his math teacher, and he's completely messing up the absolute value description. What he's based, he described it in pretty much a wrong way. And what he said is you take the absolute value of a number, if the number's negative, make it positive. And if the number's positive, keep it positive. That's absolutely wrong. What the absolute value does is it actually strips off the sign. There's two parts to the number, remember? It's the magnitude and the sign, S-I-G-N. The purpose of the absolute value is to literally strip off the sign part of the number, where all you have is the length. If I were to tell you I'm 6'1", I don't tell you I'm 6'1" pointing to the sky, or I'm 6'1", pointing to the ground, or there's no direction to my height. Literally, I get onto a scale and I literally figure out, okay, from the bottom of my feet to the top of my head, that is the length of that measuring tape. It is 6'1". There is no particular direction to it. It is nothing but a length. And that is what's going on here. So when I take the magnitude of x1, it is literally 3. It's not plus 3. It's 3. It is the magnitude. If you're to ask me, Professor Mark, can you draw me a vector of magnitude 3? I would say, well, I don't know. I have a 50% chance of getting it right. Because I might draw this vector, or I might draw this vector. I might draw a vector going from the origin to +3, or I might draw the vector going from the origin to -3. And in either case, when I take the absolute value, I strip off the sign and I get 3. If I take out my measuring tape, the length here is 3. The length here is 3. So again, the magnitude is the length. All right. And so we have the position. So x1 is considered the position. So x1 is +3, the position. We'll call it the initial position. Well, let's say, for instance, that, and again, I don't know how things move yet because we haven't gotten that far in physics. That's a chapter 2 thing. But let's just say, that an object moves for whatever reason, and it moves out to, say, 6. And again, it's a little harder to draw in one dimension because I end up drawing vectors on top of themselves. But let's say I will start off at x1 is 3, and then it moves over to a new position. And now I would draw the vector from the origin again. In this case, x2 is +6. x1 is +3. Both vectors are drawn from the origin. And I say, okay, my final position, x2, is +6, the final position. Now, again, at this state of the class, next week we'll learn how things move according to what's called kinematics. For right now, we're trying. I have to put the cart before the horse. And so let me do something. I don't know how good this is going to be for students looking at this whiteboard, but let's just imagine that I'm going to color x6 green, or x2 green. And so instead of, you can kind of get an idea that there actually is, a vector on top of a vector here, right? I mean, I'm literally going to go from 3 to 6, but my initial position is going to be from the origin, +3. My final position is going to be from the origin to +6. And I want to ask myself the question, Well, can I describe the difference, or basically the difference in the positions from the final position to initial position? Yes, I can. I call this delta x. And that's going to be x2 minus x1. Okay, this is called the displacement. Displacement is a difference of vectors. In this particular case, I'd say, well, what is my final position? Well, it's plus 6. Again, I'm being very, very deliberate here. Minus, it's an algebraic minus a plus 3. And what you're going to find out here that the answer is going to be a plus 3. That's my displacement. Yes. Plus, I went, this is a positive 3 difference in vector. This capital's triangle, if you haven't seen it before, is the Greek delta. It's a capital D in Greek. Looks like it looks like a equilateral triangle, but it's actually a Greek letter. In English, we use the capital D. In Greek, it's delta. Delta basically means a difference in. So we have what's called a displacement. All right. So displacement is essentially going to be the change in position. All right. So, and again, I don't want to talk too much about the actual physics until we get face to face next week. But a displacement equals change in position. When you see the letter delta, that means change in or change of. It means change. All right. So that delta means change. I mean, so now turns out that if I add or subtract vectors, I get another vector. So the displacement is actually a vector. All right. So if you add or subtract vectors, you get another vector. So the sum or difference of vectors is another vector. Two vectors add up, make another vector. One vector subtracted from another vector, again, gives you a vector. And it's very important. Now, we have special names for some vectors. So again, we know that the change in position is a displacement. There's a special name given to the magnitude of displacement. That's called the distance. All right. So again, the magnitude of the displacement is the distance. All right. And we'll talk, next week we'll talk about the change in position with respect to time. That's called the velocity. The magnitude of the velocity is the speed. It's another special name. Again, we're not talking about that today. That's a next week topic. But again, there's certain things that have special names associated with them. Okay, so let me ask a little question here. What happens if, for instance, I decide, and I oftentimes will be in front of the class and I'll demonstrate this just physically, but let's imagine that you're looking at me in front of the class. I'm doing a little experiment for you. I'm saying, okay, you know what? I'm going to you can watch me start off what I call what I call 0. And I'm going to move over to some x1. And I'm going to move back to where I started. To some x, basically, I'll say this is my position x1. And then I go back x2. And I ask you, what is the distance? Okay, again, I started at some spot. I moved a certain distance. And then I move right back to where I started. Anybody want to venture what my distance is? Anybody there?
Is it 0?
It is 0. Doesn't matter that I actually walked a whole bunch. It's not the reading on the pedometer. Literally, x1, literally x2 minus x1 is going to cancel out and give me 0. Now, if you want the distance that you'd measure on a pedometer or an odometer, you would say that's called distance traveled, not distance. Distance traveled is the total distance as measured by, say, a pedometer or odometer. Either you're walking or you have a car. That's distance traveled. So clearly, I'm going to get my steps in. I have so many steps or so much distance. I'm going to come back and I have so much distance. That's called distance traveled. Distance is literally final position minus initial position. And so my final position and my initial position are both at 0. And so the whole thing is going to be 0. Doesn't matter that I may have walked a mile this way and a mile back. The fact is, all that matters in physics in this particular definition is the final position and the initial position. And they happen to both be at 0. So it'll be 0 minus 0 equals 0. Doesn't matter how far out I went. Otherwise called distance traveled. All right. So it's just it's a little confusing to talk about distance sometimes. So any questions? Okay. Let me go to 2 dimensions now. We have about an hour to go. So let me now venture into 2 dimensions. I think 2 dimensions will be a little easier to see. Now it's a lot easier for me to teach the 2 dimensions when I have a full whiteboard. So there's going to be a little challenge on this. So bear with me. So in 2 dimensions, what we're going to talk about is a vector that now is going to be defined in a 2-dimensional Cartesian system. All right, so instead now, I have to define my vector in terms of an x and a y. And maybe I'm locating that fly that I was talking about. And let's say this is my origin. X equals 0, y equals 0. And I will essentially draw a vector. This is like we're talking about positions tonight. I will draw a vector from the origin out to where my object is. All right. And maybe I'll call that R. And I'll put a little vector hat on it. Now, the question is, if you were to ask me, let's just say that for instance, that the magnitude of R is 3 meters for whatever reason. And so I have this vector and I say, okay, you're to ask me, Professor, can you draw me a vector in two-dimensional space that has magnitude 3 meters? Now, if you ask me that question in a one-dimensional space, I would look at you confused. And I'd say, well, I have a 50-50 chance. In one dimensions, I have, in 1D, I have what's called a twofold ambiguity. So essentially, that's a fancy way of saying, well, I don't know, I have a 50-50 chance of getting it right. I have two possible answers to that question. Let's say +3 or -3, but I need more information. You have to, you really have to specify what the direction is. Is it positive or is it negative? You can't just tell me that you have a vector size 3. Okay, in 2 dimensions, this is much, much, much worse. In fact, it's infinitely worse. If you're to now tell me in 2D, I want you to draw me a vector of size 3 meters. I'll look at you and say, well, I really don't know, because I have an infinite number of vectors that I can draw. Literally, if I think of this as a spinner, any position that this particular vector can take in the entire circle is a possible answer. So you're going to have to give me some sort of a direction. And typically, that's done by giving me an angle. So that's the Greek letter theta. All right. So I have an infinite fold ambiguity here. I literally have an infinite number of possible vectors that I can draw, and you're going to have to help me out here and tell me which one of these infinite numbers it is. And so you do that by giving me an angle. All right, so that
Professor O'Callaghan,
uh-huh.
I have a quick question about
Sure.
the different dimensions, I guess. So
Sure.
if it was in one dimension, of course, it could only go either positive or negative, like it would
That's right.
have to go one direction.
Yep.
And so I get that. And then 2D, I get that it could go anywhere in that circle. Does that or that graph, if you will. But if you were to, does that change if that were in 3D? Like if it could come out, like let's say that vector could come straight out at your face or straight out away from you, then would that be, is that possible? Is there a third dimension, I guess?
Sure. Absolutely. In fact, in three-dimensional space, and again, this gets kind of beyond what we're talking today, but in three-dimensional space, you have really about 3 different angles you can actually specify. So I can put a vector in three-dimensional space, and then I can make an angle with respect to the x-axis, the y-axis, and the z-axis. So these are actually they're officially called direction cosines. And so literally, you're a little kid saying, I know more than you by infinity. And the other kid will look and say, well, I know more than infinity plus 1, right? And the idea is, well, it kind of makes no sense to say infinity plus 1 is just infinity. And so if I have multiple dimensions, like 3 dimensions, it's just going to be a bigger infinity, if you will, but it's still infinity. And so it'll be an infinite fold ambiguity, and you literally would have to specify. Now, I think my answer will make more sense as I progress tonight in the class and talk to you about what are called components of a vector. Because what I need to do is I need to figure out, if I'm going to specify this vector, I need to figure out how much of it is in the x direction, how much is in the y direction. And so the x direction has an infinite number of values, and so does the y direction. If I were to draw, let me try to make this picture a little bigger so I can try to answer your question while I move on to the next topic here. If I were to make this bigger and I were to say, okay, I really want to understand, I have this vector R. Well, if I were to draw a vertical I can call this R sub X. I can call this R sub Y. For right now, these are just numbers. I have an infinite number of values between this number and whatever R sub Y is. There's an infinite number of real numbers also between the y-axis and this vertical leg of this triangle. So again, there are an infinite number of ways, infinite number of x values and y values. Now, if you go into 3 dimensions like you're talking about, you would also have z values. And so again, there is an infinite number of ways to specify that vector as well. Does that make any sense? Did I
Yes,
answer your
it does.
question?
Thank you.
Yeah, absolutely. So this gets me kind of to the next topic. And that is, I have a couple different ways to specify a vector. I'm gonna make this even bigger. And my whiteboard's limited. There are 2 ways to specify a vector. One is a magnitude and a direction, which I kind of showed you a moment ago. Tell me how big the vector is and what is theta. Sorry, I have this little light that I'm fighting here. The second one is components. Right? We don't know what components are quite yet, but we do see that there is a magnitude and direction. I can understand the vector is going to have a certain length and a certain angle. Right? What I really want to understand in order to be able to actually be able to add and subtract vectors, because one of the things you have to do is, you learn this when you're in elementary school and in junior high and stuff, is you have a new mathematical object, for instance, like a real number. Okay, great. I have a new object. I have a new mathematical object. What do I do with it? Well, I want to know how to add, subtract, multiply, and divide it. I'm going to tell you how to add and subtract tonight. Multiplication is a little more difficult. I'm going to leave that for a few chapters. All right. And so, and in fact, there's really no such thing as subtraction. Subtraction is the addition of the opposite. And there's really no such thing as division either. Division is multiplying by the multiplicative inverse. So all we really have to do in mathematics is add and multiply. Okay, so let's understand when I'm talking about component form, what do I mean? All right, so let's talk about writing a vector in component form. Okay, so again, I go back to the Cartesian coordinate system. I'm going to try to write this out as well as I can. And let me draw position vector, call it R with a hat on it. Now, one of the things I'm going to invoke in my reasoning is there are about 8 different coordinate systems in physics that are called orthogonal coordinate systems. We're only going to cover at most about 3 in this class. So an orthogonal is a fancy word. An orthogonal coordinate system is one where the coordinate axes meet at right angles. This is not to be taken for granted. What this means is one example is the Cartesian system. And there's about 8 altogether. That means that I know that the X and Y axes are orthogonal. They meet at 90 degrees. All right, I'm gonna utilize that fact when I do component form. Another one we won't talk about until we get to chapter 5 is spherical polar. And and you pick a coordinate system because it has a certain symmetry. So something's like a circle or a sphere, use spherical polar coordinate systems. And if something, let's say, for instance, is naturally is on like a can, like a soda can, we also have one called cylindrical systems. We're not going to use that in this class. So yeah, cylindrical coordinates. And I mean, and there's another one called, like in my book that I'm writing, I utilize what's called elliptical coordinates as well. Why? Because I'm talking about a diatomic molecule, and I can actually put an atom in each foci of an ellipse, and I can define it in a very, very nice way in terms of elliptical coordinates. But again, that's a very unique system. But again, why do I do that? Because it's advantageous for me to do so. We'll realize that we pick a coordinate system that's actually useful to us, and it actually is advantageous. Nature's going to do what nature's going to do, irrespective of what we humans, our observers, do or see. Nature's still going to do it. So we can do ourselves a favor and actually use a coordinate system that is advantageous or convenient. So when I draw coordinates, given that I know that the Cartesian systems are orthogonal, I can drop a vertical, and I know that vertical is going to also be orthogonal. It's also going to be at right angles because I'm using an orthogonal system. So this means I can write a right triangle, and I can have so much of my measure in the x direction, I call it r sub x, and I have so much of it in the y direction, I refer to that as r sub y. Now, let me state what I'm saying. When I say r sub x, I'm saying that's r with the subscript x. R sub y is r with the subscript y. My vector is r, but r sub x, when I say r sub x, it's r with a little subscript x. And I literally will call it r sub x. Basically meaning that's the portion of r that is projected onto the x-axis. And when I say r sub y, I'm literally saying r sub y. That's the portion that's in the y-axis. So my vector is so much x and so much y. Now the question is, do I understand how to find r sub x and r sub y? Now, we hypothetically understand that I have that I know r and theta. So I know the magnitude of r. Let's just call it 3. And 3 meters, 3 whatever, it doesn't really matter. Because vectors are used for forces and electric fields and so on and so forth. Right now, I'm just going to worry about just the math. Let's say my theta, I'll pick a nice angle like 30 degrees. Okay, so I know, now I took the hat off. When I take the hat off, that means it's magnitude. When I put the hat on, like right here, it's a vector. So taking the hat off means I'm talking about the magnitude of that vector. And so this is what I'm given. I'm given that r equals 3 and theta equals 30 degrees. Now, I want to understand what r sub x and r sub y are. We're barely in chapter 1. We already have to do trigonometry. And so I look at my right triangle and I say, okay, well, I got to remember, again, I'm going to go, some of you may have had trig last year, and some of you may not have had it for 10 years. So understand, I'm going to try to teach you the common denominator. So some of what I'm about to say may be a little slow, and for those who might be bored for a moment, that's okay. I mean, just, understand some people may need more of the refresh than others. So if I look at this triangle and I say, well, I have this triangle here, this right triangle, and my angle theta, well, if I look at r sub x and I say, well, I know SOHCAHTOA. You guys remember that? SOHCAHTOA means that so is sine. And that's opposite over hypotenuse. Ca is cosine. Adjacent over hypotenuse. All right. TOA is tangent. And that is opposite over adjacent. All right. So sine, SOH, sine is opposite over hypotenuse. Cosine, the CAH, cosine is adjacent over hypotenuse. TOA, tangent, that's opposite over adjacent, TOA. All right, just to remind you, that what we're talking about here, we're going to have to use trig functions right now. All right, and so here we are, barely in the second day of lecture, and we're already needing trig. All right, so I want to use trig functions, and I want to try to figure out how in the world I can express my r sub x and r sub y. I'll do the first one for you here. R sub x, well, let me ask this. I have this leg and the hypotenuse. What do you think I should use? Should I use cosine if I'm talking about r sub x, or sine or tangent?
Cosine.
Well, let's see. Cosine. All right, let's see why that is. Cosine of theta. Remember, it's adjacent over hypotenuse. Cosine of theta. Okay, my adjacent basically means, it's a fancy word for next to. The person sitting next to you is sitting adjacent to you, as opposed to somebody sitting across the room. So adjacent and again, everything's with respect to this angle. This is the leg that's not the hypotenuse that's closest to you. This leg is opposite to you. So r sub x, so the adjacent in this case is r sub x. The hypotenuse is r. I will cross multiply, and I can write that r sub x is r times the cosine of theta. So on the right-hand side is stuff that I knew going in. Those are givens. I know theta and I know r. I put cosine theta in my calculator, and I multiply it by r, and I get r sub x. All right, so I'm able to express, new components. I get what's called the x component. R sub x is the x component of r. All right, and so I know how to figure that out. So let me kind of put this in my parking lot here. So again, I'm just going to kind of collect this information. So r sub x is r cosine theta. I'm doing this because I have little space. I need to know r sub y. So r sub y, I'm going to use the sine function. How do I know that? Well, that's the leg that's opposite to the angle. So sine of theta is the opposite over the hypotenuse. So, SOH. On my opposite is r sub y. And hypotenuse, again, is the magnitude of the vector r. I will cross multiply. So let me write this out again. So sine of theta is r sub y over r. Cross multiply. I get that r sub y is r times the sine of theta. Okay. R sub y is the y component of r. So again, that's why I'm calling it component form, because I have to express the vector in terms of components. Any questions at this point? Okay, put this in the parking lot. So R sub y is R sine of theta. I need to know that now too. I'll try to erase the rest of this stuff. All right, so now I started off with just the magnitude and direction. Now I have components. Now I'm going to give you a concept that is generally not in your book, and you may but it's something that's in many physics books, and it's called unit vectors. Unit vectors are vectors that basically have magnitude 1, so they don't affect the magnitude of the actual vector, and their whole job is to point along the coordinate axis. So a unit vector is a vector of magnitude 1. Whose job is to point along a coordinate. All right. And so basically I would have what's called X hat and Y hat. All right. And I have to use these little party hats on the vector. And it's different than the hat that you've seen for the vector, right? So my unit vectors for Cartesian, at least in two-dimensional Cartesian, I'm going to refer to as X hat and Y hat. So X hat, I literally will pronounce it as X hat. That's how the physicists say it. Y with the party hat, Y hat. All right, X hat's job is to point along the x-axis. You know, basically, oh, the vector's going this way along X or negative along X. Y hat's job is to point either the vector is going to be going positive Y, negative Y. So in this particular case, for this vector, it's a first quadrant vector. That means it has a positive X and a positive Y. And so it would actually have positive unit vectors in both cases. So if I were to draw out the full vector in component form, I would say that R, the vector, is R.
Excuse me, Professor.
Yes.
You say about the X hat and Y hat.
Yes.
If it's negative, it's the same. Like how you know that it's Y negative or X negative?
Right. Let me continue, and I think it'll be I'll answer your question as I go along. Is that fair?
Yeah, fair.
All right, so let me kind of show you that to you. So that's a very good question, and I'm about to get there. So when I write this vector out, I would say that the vector is, as I said, it'll be R sub X, X hat, plus R sub Y, Y hat. All right, and so now R sub X is just the magnitude, how much X hat. Now in this particular case, I have a first quadrant vector. That means that I will have a positive X and a positive Y that gets me there. What if I had a vector like this? Let's say instead this was my R. Well, here, now this is a fourth quadrant vector. Positive X, negative Y. Right? In order for me to draw that vector, I would go positive along X. It's kind of like if I'm going to go to Tomorrowland or something, right? I mean, I go this far to the right, but now I got to go down. So now I'd have a positive X hat, but a negative Y hat. My Y vector would say, well, yeah, you have this much R sub Y. That's a magnitude. Which direction are you going? Are you going up or are you going down? Well, I'm going down. For X direction, I have this much magnitude R sub X. Is it to the right or to the left? Oh, it's going to be to the right. Why? Because that's a fourth quadrant vector. I could also have a vector like, say, let's do a third quadrant vector. There's X, here's Y, and let's say I'm down here in the third quadrant. Now what do I do? Well, now I got to go negative X and negative Y, right? This is my R sub X, the length of my leg. This is my R sub Y, but then now I got to tell you, which direction are you going? Well, again, now this vector is living in the third quadrant. So it's going to be negative X hat, and it's going to be negative Y hat. I have to go left, which is negative, and I have to go down, which is negative. So to answer your question, the job of X hat and Y hat is to basically tell me which direction are you going. I know how big your magnitude is, I know the legs of your triangle. The question is, are you going to the right in X or the left in X? Are you going up in Y or down in Y? Those are the questions that are answered by the unit vector. So if I were to decorate this thing in its full glory, what R sub X and R sub Y is, then I know what R sub X is. I know what R sub Y is. I figured it out already, right? So R instead of R sub X, well, that's really going to be R cosine theta X hat plus R sine theta Y hat. All right. Now, I know in this case that X hat and Y hat are both positive because I gave the most basic example possible of that. Now, let's kind of work out what these numbers are. So R cosine theta, so R sub X, let me kind of make these numbers now. R cosine theta, well, I told you that that's 3. I gave you R is 3. And cosine of 30. Well, when you go take the MCAT, right, you're not allowed to take a calculator to take the MCAT. You have to remember certain angles. So you need to remember what cosine of 30 and sine of 30 are. Sine of 30 is a half. Cosine of 30 is the square root of 3 over 2. And then sine of 60 is the square root of 3 over 2. Cosine of 60 is a half. So there's these little things you have to kind of remember. So the cosine of 30, I have 3 times the square root of 3 over 2. Again, you can just plug in your calculator. If I go to my calculator here and I type in cosine 30, I would actually get a big long number, 0.866. Well, that's the square root of 3 over 2. Multiply that by 3, I get 2.598, call it 2.60. So about 2.60, roughly. If I were to say R sub Y, that's R sine of 30. Well, this is going to be 3 times the sine of 30. Well, sine of 30 is one of those numbers you have to kind of remember. That's a half. Sine of 30 is 0.5. So that's 3 times a half, or 1.5. All right, so now I have numbers. So now what I can say is, oh, okay, let's write what this vector really is numerically. R is 2.6 positive, this is positive Y hat, X hat, 2.60 X hat plus 1.50 Y hat. So that is the component equivalent of a vector size 3 at 30 degrees from the positive x-axis. Okay, I literally went from magnitude and direction to component form. This is an equivalent way of stating this. Okay? So, any questions about that? This is the method you use. And again, we're going to have a whole vectors lab in a couple weeks. I'm going to go over all this, in the vectors lab, remind you of it. But again, this is the way to go from magnitude direction to component form. What if I wanted to go the other way? What if instead I gave you this vector and I said, I want you to give me this, I want you to give me this in I'm going to give it to you in component form. I want you to give me the magnitude and direction of it. What if I did that instead? All right, so let's go the other
Excuse me,
direction.
teacher.
Yes,
The x hat and y hat still in the component form, it's not defined. We leave it like that.
that's absolutely right. It's telling you that this vector, I have two ways of describing this vector. Either magnitude in a certain direction, or this vector is so much x hat, or so much x and so much y, and the x hat and the y hat tell you what the units are. So the x hat and the y hat are actually vectors that are unit 1. If I were to take the magnitude of x hat and the magnitude of y hat, those magnitudes are 1. It's a little bit more of a theoretical concept, but they're called unit vectors because unit stands for unity. So if I were to say, I want the magnitude of x hat, that's 1. The magnitude of y hat is 1. Being that they're 1, they do not affect the magnitude of the vector. Their only job is to point. Their only job is to say, I have this much in the x direction plus this much in the y direction. And by the way, this is going to be a positive x and a positive y. The unit vectors are their job is to do nothing more than point. So I got a bright spot there, right smack in the middle of where. Hang on, let me rewrite this vector here. I see a bright spot on my computer. Positive 2.60 x hat plus 1.50 y hat. That's my answer. So that's where I don't have that big bright spot. So anyway, that is the equivalent vector in component form. So this is a vector in component form. The exact same vector that I had before. Now,
Professor,
yes.
like, so now the thing that will define if the direction of x, as you say, x and y, just to show the direction,
Yeah.
it's gonna be the only thing gonna change the sign, like plus 2.6, it's the theta. Is if the angle is for example in the fourth quadrant, or and then it's negative, like all x are negative, then it's gonna be negative, and then right.
Yeah, so let me give you an example here. Like you saw this vector here. So let me kind of write this in the parking lot for a moment. So I'm going to remind ourselves here that this vector that we just got done writing deals with this problem of r equals 3 and theta equals 30 degrees. So we got this answer. So what would happen if instead I were to have given you this problem? And instead I said, well, let's just say, for instance, forget about what I just got done doing, but instead I said, you have this problem now. Here's your R. Now you're below the x-axis. And your magnitude of R is still 3, and your theta is 30 degrees. If you went through all the math that I just got done doing, you would find out that your answer would be the following. You'd have still positive 2.60 x hat. Instead, you'd have minus 1.50 y hat. You would still do the same trigonometry. You would still figure out the same r sub x. and the same r sub y. All the trig you just got done doing would be absolutely the same. The difference would be that you would have, again, I'm right, a light again, sorry. You would have, your answer would be r is positive 2.60 x hat minus, not plus, but minus 1.50 y hat. All right. And so literally
So
all
if you
the
were
trig would be the
doing
same.
that, if you were doing that in the third quadrant, then they would both, it would be negative 2.60 x hat or minus 2.60 x hat and then minus 1.50 y hat,
Absolutely right.
right? And then
Absolutely right.
if it was the second quadrant, then y hat would be positive and x hat would be a negative.
That's
But
absolutely
it
right.
would still be the exact same numbers.
Yep. Absolutely right.
Okay.
But
Absolutely right.
how you know, like, do you, when you give the question, you specify, like, is it X in this quadrant, or like, my question is how you know it's in this quadrant, like how you know it's positive or negative.
Right. So there's different ways of expressing it. Again, this will be more clear in the vectors lab. But if I were to go from magnitude direction, I have to give you a couple. I'd have to give you a couple of, so I'd have to tell you I have r equals 3, and I have theta equals, say, something. Now I just gave you 30 degrees from the x-axis. I could have told you it's 150 degrees. What does that mean? Well, that means that you would then go out and say, okay, well, I have my r, but what's 150? Well, going all the way around is 180. So 150 means that this angle is 150. And then I like to, what I call, hug the x-axis. I like to take the angle that's closest to the x-axis so that my x component is usually a cosine and my y component is a sine. I take a look at 150 and say, oh, well, what I really want here is this angle, 30. So my angle will be 30, and I like to deal with what I call local triangles. I like to basically just have a triangle that has legs, and I figure out what the plus and minus signs are afterwards, after I get done doing the trig. So when I go and I just have a triangle that has lengths on it, I'll just do that triangle. I have a 30-degree angle, I figure out r sub x, and I figure out r sub y, and at the very end, I figure out what coordinate, what quadrant is this vector in? Oh, it's a second quadrant. So my r sub x would be, I think as Jess was saying, it would be negative. My r sub y would be positive. So I just do all the trig on a local triangle, not worrying at all about signs, because that's just going to confuse me. And then when I'm all done, I have r sub x and I have r sub y. Then what I can do is I can go back and I can say, okay, great. Let me now, what quadrant am I in? Oh yeah, I'm in a second quadrant. So my r sub x is negative and my r sub y is positive. So I figure out what the plus or minus signs are on the x hat and y hat based upon where my triangle actually is. So yes, I mean, you have to draw little pictures. I mean, and I always tell people the first things you should do when you do a problem is to draw a picture. And that way, that picture tells you what you need to know. You know, for instance, what right triangle? You know, I have a bunch of right triangles I could draw. Which one? So it's a very good point that you bring up is how do you know? Well, you know because you have to be told. So I'll either tell you it's 150 degrees, or I'll tell you maybe it's 30 degrees from the negative x-axis. I have to specify my angle. I have 8 different 30-degree angles I can draw. You tell me, draw me a 30-degree angle. I'll tell you, I don't know what you're talking about. you have to give me more information. I have 8 of these. I can draw this 30-degree angle, this one, this one, this one, this one, this one, this one, this one. I have 8 different 30-degree angles that I can draw about the positive x, positive y, negative x, and negative x and positive x, negative x, positive y, negative y. I have 8 different 30-degree angles. You have to give me more information and tell me which 30-degree angle. So I will give you that information. Or whatever problem is that you're doing, you'll get the information from that problem. You have to know that information to specifically know what kind of vector you're dealing with. Okay. So let me go.
Yes, now it's clear. It's clear. Thank you.
Yeah, absolutely. Thank you. Let me go the other way. And let's say I gave you, oops, I just erased my lot, but that's right. I remember what it was. Let's say I gave you instead a problem in component form. Now I want you to go the other way. I say, I'm giving you a vector. We know the answer to this vector already, so we can understand when we get the answer and we get the component, when we get the magnitude and direction and angle back, we'll know when we're actually right. I don't have to check it because we already know. So 1.50 y hat. And I say, I want you to go from component form to magnitude and direction. I want you to go the other way. You say, okay, well, fine. I need to figure out what this triangle even looks like. Oh, okay. I have a positive x component and a positive y component. All right. This triangle, whatever it is, it lives in the first quadrant. So I know that my triangle lives in the first quadrant because I know that the x component is positive and the y component is negative. And I know this time I know r sub x and r sub y. What I don't know is r and theta. Remember, I'm going the other direction. This time I'm giving you a problem where I'm telling you what r sub x and r sub y are. And by the way, I'm also telling you what quadrant that the vector even lives in. And I want you to tell me what is the magnitude and direction. So first of all, understand you now know r sub x and r sub y. I want to get r. Remember, I want to get r, so I want r and theta. Well, I can get r going back to geometry. I have Pythagorean's theorem. That is that r squared, the magnitude squared of the hypotenuse, is equal to r sub x squared plus r sub y squared. And I want to take the square root of both sides. So r becomes the square root of r sub x squared plus r sub y squared. So in that case, again, you're going to have to, you only ever have approximations in your calculator, but I will take the square root of 2.60 squared plus 1.50 squared. So if I go to my calculator and I say, all right, let me get 2.60 squared plus 1.50 squared, I get a number, I get 9.01. Again, this is a little bit of round off error for my calculation. I take the square root of that, I get, whoops, I get 3.0016, blah, 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 right? All that stuff, all that other stuff is basically a round off error. Essentially, to within our significant figures, I have just shown you I can give you r equals 3.00. So automatically, I know that if I have this vector, I can compute from the Pythagorean theorem that r is equal to 3.0, whatever the units are. I now need to know theta. So theta is right from a trig function. Now remember, what you're given at this point is R sub X and R sub Y. Now, granted, the more information you know, the more tools that you can use. So hypothetically, now that I really know R sub X, R sub Y, and R, I can actually find theta from any of the trig functions. But let's just kind of restrict ourselves and say, remember, what we knew in this particular case was just R sub X and R sub Y. So let's only use those, since those are given. So of course I would use TOA, the tangent. I would say the tangent of, I don't know what theta is this time, but the tangent of theta is going to be the opposite over the adjacent. Well, the opposite is R sub Y. The adjacent is R sub X. All right, so I have tangent of theta is R sub Y over R sub X. Now, of course, what you want to do is you want to try to get the theta. How you do that is you take the arctangent or the inverse tangent. So I'm going to do things very methodically here. The arctangent or inverse tangent of the left side, so your inverse tangent of theta. What I do to the left, I must do to the right. And I'm going to be a lot faster normally here, but we're just kind of, some of you may be blowing off a lot of dust on your trig. So R sub Y over R sub X. So what I do to the left, I must do to the right. And of course, the arctangent or inverse tangent undoes the tangent. And sorry, I'm right in that light spot again. All right. So let me rewrite what I just got done writing down, but avoid that little light spot. All right, so remember, I'm taking the arctangent of the tangent. What I do to the left, I must do to the right. So I take the arctangent of R sub Y over R sub X. The arctangent is the inverse function of the tangent. So what I literally just get back the angle. And I have the arctangent of R sub Y over R sub X, or that's the arctangent or inverse tangent of, let's see, what's R sub Y? Again, I just want leg lengths here. So 1.50. R sub X, that length there is 2.60. And if I work this out, let's see what my calculator says. Inverse tangent of 1.5 over 2.5. My calculator says 30.96. So again, I kind of rounded on this one a little bit. So the answer is supposed to be 30. I was a little sloppy. So it's supposed to be about 30, right? So I mean, I was a little bit sloppy. This was really 2.59 something. So I should have done a better job. But again, you get the idea that that's how you get back to your angle. So I literally can use this method to say, if I have a vector in component form, I can get to magnitude and direction by using the Pythagorean theorem and this inverse tangent. If, on the other hand, I have magnitude and direction, I can get to the component form by using the trigonometric functions using unit vectors. I can go both ways. Now, one of the things that you want to do when you have a new mathematical object is you want to add them. You know, just like when you're in grade school, I have a new thing called a real number. So I want to know how to add them and multiply them. Well, again, as I say, multiplication in vectors is a little bit tricky and a little strange at first to you. So I'm not gonna talk about multiplying vectors until we get to chapter 6. All right, so chapter 6 is one I'll give you. And there's actually 2 ways to multiply vectors. There's 2 forms of multiplication. So we're going to shelve that for the moment. But we'll talk about addition. So when I add vectors, to add vectors, you must put them in component form. So either they're in component form or you have to put them in component form. All right. And so if I have two vectors, I'll call it A. A vector A, and I'll try to do a little example of this. I'll say that's A sub x, x hat, plus A sub y, y hat. All right. So this is just, again, I'm giving you kind of a theoretical basis for the moment. But if I have two vectors, let's just say I have them and I can write them in this component form. Maybe I have to do a little bit of work to get there. Now, I could also say I have a vector B. And that vector is B sub x, x hat, plus B sub y, y hat. If I want to add them, I call this the resultant. The addition of two or more vectors is called the resultant. I want to add A plus B. We add vectors component by component. And so we're going to add A sub x, x hat, plus A sub y, y hat. And I have to erase here. Plus, second line, B. That's B sub x, x hat, plus B sub y, y hat. You add them component by component. So what I need to do is I need to arrange so that I'm adding the x components together and the y components together. So literally, whatever, now these A sub x's and B sub x's and stuff, those are numbers. And again, I'll give you an example here in a minute. A sub x and B sub x are just numbers. They will add together like scalars. A sub x plus B sub x. All in the x hat direction. Plus A sub y plus B sub y. Also all in the y hat direction. Now let's remember this, and let me give you an example. I think the example will make it easier. This is kind of the theoretical version of it, but let me give you a simple example. Okay, so I'm going to add two vectors, and I'm gonna kind of draw them out. So I'll add a first quadrant vector and a second quadrant vector. All right, and so again, there might be some work that I have to do, but well, actually, let's just go through the whole blasted thing here. So let's just say I have this might take a couple minutes. I might go a little bit over. I hope that's okay with you guys. I still need to do well. You know what? Let's just do this. I'll cover it more in the, when we do the vectors lab. Let's just say I have A is positive 2 x hat plus 3 y hats. All right, just I have a vector A. I have a vector B. I'll call it negative 3 x hat plus 4 y hats. I want to add the two. So let's just see what these even look like. Okay, I have two vectors. I'm going to add them. So I have A. Well, A is going to be, say, 2 out, 3 up. It's going to be some number that's going to, oops. Eesh. Looking like this. That's my A. I know, I'll say that's theta. I know that A is, well, this is right this way. This is A sub x and A sub y. All right, so I know that A is a first quadrant vector because it has a positive x and a positive y. My B, on the other hand, is going to have a negative x and a positive y. So negative and x, positive y. So B is going to pop over looking something like this. Again, my leg length is B sub x. My leg length is B sub y. I'm going to add those two vectors together. So I want to add, I call this my resultant. So again, the sum of two or more vectors is the resultant. That's the official term. I'm using R for that. So A plus B. And you have to tell me what A plus B means. We define it in physics. Or, sorry, that's not even physics, math. So what's my A in this case? Well, my A is going to be 2. I'll be very deliberate here. Positive 2 x hat. I'm about to, hang on. I got a little light spot. So give me a second here. I'm trying to avoid it. I want to do A plus B. I'll do this example, then we got to do roll here. So R is A plus B. So what's A? Oh, positive 2 x hat plus 3 y hat. What is B? Negative 3 x hat plus 4 y hat. All right. I added component by component. So I put the x hats together and the y hats together. So I have positive 2, negative 3, just scalars. So this is 2 minus 3 x hat. This is my A sub x, and that's my B sub x. Now, I'll put the other ones together, plus A sub y, B sub y. Putting real numbers in, so 3 plus 4. All y hat. Now I just have scalars. 2 minus 3 is negative 1. So my R looks like negative x hat. 3 plus 4 is 7. 7 y hat. That is my new vector. And that one lives also in the second quadrant. It's going to be very steep, though. If I go 1 over, I have to go 7 up. So again, it's going to be a very steep vector. That's going to be in the second quadrant. But again, I have to put him in. Now, hypothetically, this is another vector. If I wanted to continue, I'd have to use Pythagorean theorem to find the magnitude, use a arctangent to figure out what its angle is. And I would treat this vector like I would any other vector. It's just another vector. All right. And so that's as far as I want to go today. I want to go and put a little time aside for roll. But what have I talked to you tonight about? I mean, I've talked to you tonight about units, and I've talked to you about vectors. And I've given you specific examples of these. And so there's not very many problems I'm going to assign. But again, that's what I talked to you about today. So so give me a moment here. Let me do roll real quick, and then I will put this on YouTube again. So any questions in the meantime? Is everybody still here?
Yes.
Excellent. All right, so let me
I do have a question about homework.
yes.
Is there a day of the week that you'll assign the homework?
I'm gonna assign the homework tonight. So when I get done with so I say as I said on Tuesday, I know this has been a difficult week because you haven't actually met me before. But when I assign homework for a given week, so I'm gonna consider that we completed chapter 1. And we're gonna do more vector stuff. We're gonna have a vectors lab. So you will have vectors coming out your ears in this class, so don't worry. I will assign the homework tonight for chapter 1. And again, I'm also going to assign the lab. Again, as I said, the homework for a given week is due the Wednesday of the following week. So homework, that I assign will be due tonight, will be due next Wednesday. You'll see that popping up on Canvas. The lab for a given week is due the Thursday of the following week. Again, you'll see the lab popping up on Canvas tonight as well. So there won't be very many chapter 1 problems. It's going to be no more complicated than what you saw here. And I do have a vectors video as well. So I can point that out to you in the announcements as well if you feel like you want to have a little bit more time with the virtual me on the YouTube. Again, I will be physically present the rest of the entire summer. So, again, I'm sorry for this, for this, might be on travel here in the beginning of your class, but again, that's not gonna be true any longer. So, hope that answered your question.
It does, thank you.
Absolutely. So let me, hang on, I gotta push some buttons here and get to the roster. So bear with me here.
For the first couple of weeks of homework, are you able to post like the actual textbook pages? So that way we have access to them? Because I know my textbook's taking at least a week to get here.
There is a copy of the textbook in the bookstore. I'm sorry, not the bookstore, but the tutoring center. The problem is if I reproduce pages, I might be violating copyright laws. So I'm pretty careful about that. I could try. Well, I guess for the homework problems, it wouldn't be so bad. So maybe I can do that for the homework problems, maybe this time around. So maybe I'll try to do that. I probably won't be able to give that to you until like tomorrow. I don't know if that's okay. But like I said, I don't know how much more time I have going on tonight, but I'll try to do it tonight. But like I say, I understand your books are still coming and stuff. Just let me does that help? Is that okay?
Yeah, that will be helpful. Thank you.
Absolutely. Yeah, I'm kind of like running around here, so. All right, yeah, trying to set the time here.
Professor, you cannot make the first homework like available maybe on Monday next week because this week we didn't have the chance to meet and then people waiting on the book and we didn't
Yeah,
really
I can push it back a
finish.
week. That's a good point. I can push it back. Maybe I'll push it back to let me get my calendar here. Yeah, that's a good point. You didn't face to face and it's the first week. Good point. You'll end up having two homeworks due at the same time though, so be careful. Yeah, so let's kind of talk about that. I'll put that on announcements as well. I don't want to be going too much overtime here with you guys, but I'm looking at my calendar here. So I'm looking at so next Wednesday is the 5th of June. We can push it. I can push this homework to the 12th of June. But remember, you'll have chapter 2 homework on doing the 12th of June as well. So understand that. So yeah, you're working through it and you're waiting on textbooks and stuff. Chapter 1 homework will be small, but I'll push it back to the 12th of June. Does that work better for everybody?
Yeah, thank you, sir, for me.
I'll remember to do that too. So the lab I'll still have due next week. I mean that one there, you have access to the lab from all right. So let me quickly go through the roll here. So Nathan Copy. COPPI, Nathan Copy. Okay. Dorian Crutchfield.
Present.
Okay, thank you. Win Ho.
Here.
Okay. Jessica Kaiser. You went by Jess. Sorry, I'm sorry about that. So Jess Kaiser.
Yeah, that's fine. Either way, doesn't matter.
Okay. I'm gonna try to call you how you prefer to be called. Kristen Kidd.
Here.
All right. Alana Kukenol.
Here.
Brian Lee.
Here.
Is that Lee or Lay?
Lei is the correct pronunciation, but Lee,
Lei.
I've been going by Lee.
Okay, I'll try to call you Lay. I apologize. Kathy Lay.
I'm here.
Excellent. Morgan Mohan. Morgan. No Morgan. All right. Gabriella Marasano.
Here.
Ruth Moaco.
Present.
Gabby Nguyen,
Here.
all right. Sarah Player,
Here.
Vanessa Rios, Vanessa, Wolf Schweitzer,
Here.
Leonardo Servin,
Here.
Chloe Simmons,
Here.
Kat Velez,
Here.
Huang Vu,
Here.
and
Vanessa
Ella
Rios
White.
just
I'm
said
sorry,
that
what?
Vanessa Rios
Yes.
in the comment in the chat box. She said she was here.
Oh, she is. Oh, okay. Maybe her microphone's not working. Thank you. Sorry, Vanessa. I'm not looking at my chat right now. I'm looking at my. I got you as present. Sorry about that. Thank you for telling me that. Huang Vu.
Here.
Okay, and then Ella White.
Here.
Great. I think I had one person I missed. Morgan Mohan. All right. And Nathan Copy. All right. Well, thank you all for and I'm sorry about the roughness of the first week. I'll get to the appropriate assignments and stuff. I'll get those out now. And like I said, I'm going to push back the first assignment a week, for delay of books and also for the fact that this week, you haven't actually physically met me. So that's going to change next Monday. So again, sorry about that. We'll be face to face the rest of the term. Any other questions before we sign off?
Will you still give us kind of what our homework over chapter 1 is going to be? Because I do have my book and I just wanted to get started on it, so I'm not
Yep.
getting too behind.
I'm going to sign the homework pretty much in a couple minutes. I'm going to sign that right
Okay,
now.
perfect.
And then so that should take me about a minute or so. And then like I said, I'll make that a June 12th due date, and I'll officially sign the lab as well. So all you'll have due next week is the lab. Now, when I say all you have due, that lab, if you haven't looked at it yet, that lab is non-trivial. So there's a lot to it. Some people now, one of the things I want to point out too is the tutoring center is very useful. And so I would definitely make use of it if you can. That is something that that a lot of people have gone and gotten help. And so this assignment, this data analysis assignment, again, it's something that I would meeting face to face or whatever. I would not actually cover this in class. This is one of those things that the school just kind of wants to put across that this is the math you need to have in order to be able to be at the college level science. So this is unfortunately you're getting it in my class, and unfortunately you're getting it at the beginning of the semester. So I'm sorry about that. That's true for every Physics 1 class, and I apologize ahead of time because it gives a bad impression of the class. I don't want, but remember, if you didn't do so well in this data analysis lab, I mean, there is going to be an extra credit where you can completely make up a bad score with 100%. Not to say you're going to get a bad score, but again, I'd be working on this data analysis lab if I was you. So any other questions?
Dr. O'Callahan, for next
sir.
week, lecture and lab, is there anything that we can do or bring to prepare for class or in lab next week?
Not really. I mean, I'm assuming in this class, I assume zero knowledge of physics. And so we are going to literally develop kinematics, or develop the actual physical parameters, position, velocity, acceleration. So as you go along, I mean, I guess what you could do is you can kind of look at the lesson plan and see what it is we're going to cover. You can read the chapter ahead of time. That's probably the best thing you can do. But like I say, I assume no knowledge in the class. I mean, I'm going to teach you all the stuff. And honestly, if I was you, I'd rather go by my notes rather than the textbook. I don't think the textbook's all that great. My notes are going to be all that you need, all you really need. But I would say, you know, I would, and the labs next week, we'll have the measurements lab and the uniform accelerated motion lab. So again, for all of you, I would read those labs as well before the lab time. You don't have to do the pre-labs or anything like that. Again, you're going to be in a group. So next Tuesday, you will actually form your group. You'll meet each other and you'll just form a group. Some of you might already know each other. Some maybe you don't, but, you know, chance to make new friends, but you'll form your group and work from there. So yeah, I would just say, especially this summer, you're going to be busy enough just doing the homework and stuff. The class is going to go quickly. And so I would say that's probably about it, but maybe read the chapter at the most. I don't know if that helps or not.
Yeah, what about labs? Do we need to bring any graphing paper, protractors?
All that will
Okay.
be provided in the lab. So protractors will be provided in the lab, straight edges, graph paper, all that will be provided in the lab.
Awesome, thank you.
Yeah, no problem. Any other questions? So you guys are free to go if you want to. The class is over for tonight.
Okay, have a good night. Thank you so
You
much.
too. Absolutely.
Thank you.
Thank you.
See
Have a
you-
good
see
night.
Good night.
Have a good night.
See you face to face next week.
Good
See you next
evening.
Monday.
Thank you.
Bye-bye.